Okay guys, welcome to part 3 of this video, emission spectra and electron configuration. If what I will explain here is complicated and you don't understand, you can go to the part 2 of this video and part 1. So in part 1 we are starting the topic, part 2 more about the emission spectrum, part 3 I will get deeper and explain in more depth. Now, this is part 3 of this video of this emission spectra / electron configuration. Okay. Now, here we are talking about a little bit of math or more the relationship between the speed of light, the wavelength, and the frequencies. Okay. Something that I explained and defined in the videos before. Here we have something in particular. It is the relationship, the equation, and this is the one that we will be manipulating in order to solve our exercises. Here we have the following. I was looking for a different color. This is the one that I want. Something that I explained before. Meters is called the frequency, as mentioned. The shorter the wavelength, the higher the frequency. And makes sense, because if this is shorter and it has the same speed of another wave, will pass faster. Blue light has a higher frequency than red light. Something that we explained in the previous video over here with this picture. And this is blue, and this is, what is the color? They say red. You see? Here we have more energy, more frequency, and a shorter wavelength. Okay, let's come to this equation. Speed of light equals the wavelength. Remember that wavelength is the distance between crest and crest. Okay, wavelength. And the frequency would be the number of waves that pass a particular point in 1 second. The frequency. Now, understanding what is the speed of light, what is wavelength, and what is frequency, we can determine one of them if the other are given. The speed of light is always given because it is a constant. The constant that we will use is this one. Speed of light is 3 times 10 to the power of 8 meters over seconds. Sometimes you will use this speed of light in different units. That's why we'll have a different number. And in that case, we will use 3 times 10 to the power of 8 meters over seconds, because that's the one that we use in IB, and this is the one that is in the data booklet, and this is the most likely we use in chemistry in general. This formula, C equals wavelength over frequency. If I want to calculate the wavelength, I just put wavelength equals speed of light over frequency, and this will be the wavelength. Yes, this is the formula to determine the wavelength. And what about if I want to determine the frequency? It will be the speed of light over the wavelength, and then we have the frequency. Here we have the formulas to determine the frequency and the one that we use in order to show the speed of light. Here is just a summary of the high frequency and low frequency. This is something that I explained you before, but this picture can illustrate that phenomenon in a very good way. You see? Low frequency because the wavelength is big, and this is a high frequency because the wavelength is short. The shorter the wavelength, the higher the frequency and higher the energy. Okay. Here we have emission and absorption spectrum. In video number 1, in part 1, I explained how the atom is absorbing energy and is emitting energy, and what is happening with the electrons in terms of electrons. Here, I want to show you with these pictures in a general term what it means emission and absorption of a spectrum. So let's say that we have a sample with a high energy level. One example of a sample in a high energy level. If you look at the lights in your apartment, yes, the ones that you have, these bulbs are filled with gas, helium, xenon, and some combination of gases. The electricity is making the gas or the atoms of the gas get excited. In that moment is when the electrons are jumping, and at the same time some electrons are falling down. Some absorbing, some emitting. But in average, we can see the light because a lot of atoms are emitting. Now, this sample high energy is the one that you can see in your bulbs, and this is the one that is emitting. If we put a prism, it's diffracting the light. So if you put a prism and you could see through the light, you will see how the white light will be divided in different colors. So this sample of high energy is passing to a prism, and this prism is divided depending on the spectrum of the emission of that particular gas, meaning that this is emitting these particular frequencies, this frequency and this frequency. They are emitting. Those are electrons occupying discrete energy levels. They are emitting only in those frequencies. Now, what does it mean? It means that every element will produce an individual particular emission spectrum. It's like fingerprint. They are not the same for all of the humans. That's why it is a way to recognize or classify. In this case, will be the emission spectra provided for a particular gas. If the gas is emitting in these particular frequencies or wavelength, this same atom is absorbing energy. If you see, we are filling the gaps here, and this is a match. You see how they are matching here? So the absorbance spectrum is matching the emission spectrum, meaning that if the sample is emitting these frequencies submitted to high light, this same sample is absorbing energy, but only in these ranges. It's absorbing all of these frequencies. This is all the absorption frequencies of this particular gas. Or this will be the emission spectrum. Look at this. And here we have different wavelengths. Here we have different wavelengths, different frequencies as well. But this is the wavelengths. Now, here we could see how an atom is emitting or absorbing a specific frequency, like a fingerprint. As I mentioned before, electron is excited, so jump to a higher energy level, and once it gets to a higher energy level, this electron falls down. When an electron falls down from the excited state to the ground state, light of a specific frequency is emitted. This is the part of the emission and absorption spectrum. Let's continue. Okay, guys, after this, I mentioned that electrons occupied a discrete energy levels. Before, we talked that the energy is traveling in waves and is oscillating. There is not stopping, it's just traveling in the speed of light with a particular wavelength and a particular frequency, the speed of light, of course. And this is how we understand how the energy is traveling, okay? But when we talked about discrete energy levels, we are talking about that, for example, this atom is emitting in a specific amounts of energy, meaning that this energy could be quantified. And here is when more equations showed up. Here we have that the electron, when we say delta of the electron, is the difference between the higher and the lower energy. So when the electron was excited, it gets to a highest point, and then when the electron is falling down, it gets to a different energy level. This distance, or this jumping, or this falling down, is called, or could be produced in an equation as the delta of the electron, the delta energy of the electron, which is equals energy of the photon. When we talked about photons here, we are talking about quantums of energy, so we can quantify the energy. So this delta of the electron, this jumping, is also quantified and could be insulated as the energy of the photon, okay? So then we, depending on the quantity of photons, we can also give an idea of what is the amount of energy in a specific problem, in a specific situation. The energy of the photon is also related with a constant that I will mention in a moment, and the frequency, the one that we talked before. This h that we have here is none other than the Planck constant. So the Planck constant is making this relationship between the energy of the photon and the frequency. That's why the units are joules over seconds. This is a number that will never change, but this is the number that we use to change from a frequency to energy of the photon. If we know already the speed of light and we have the frequency of the photon, for us will be easy to calculate the wavelength. Same, if we have the wavelength and we have a speed of light, it will be easy for us to calculate the frequency. We will solve these exercises when it comes to practicing the past papers, especially in the Eshel level. So in the future chapters, when we explore electron configurations, there will be insulated questions about this particular part in calculating the energy of a particular atom. And then we need to calculate with moles and with more units. In summary, this energy of the electron equals Planck's constant times the frequency. And this is the equation, the one that we learned in order to solve different exercises. Okay, that will be these equations. Here we are using the Planck constant. If you want to go deeper in this topic, in the shell material. Okay, let's continue. Here we have the line emission spectrum of hydrogen. To wrap this up about the emission spectrum and the equations. So this is part 4 of this emission spectrum / electron configuration. So I will get into this in the next video. So make sure that you are following. So first, we talked about the emission spectra. We get to the lab practice to explain how atoms absorb and emit. Then what is the wavelength, what is frequency, how the energy is traveling. Here I am explaining how spectrum electromagnetic radiation is traveling using y and x axis. Then we compare that with our daily life activities, or one way to compare these sizes of the wavelengths. The complete some equations that illustrate the relationship between speed of light, frequency, and wavelength. We talked about the emission absorption spectrum. We quantified this energy of falling down or jumping with this equation of the electron equals the energy of the photon. And the energy of the electron could be calculated using the Planck constant times the frequency. In our next video, we will talk about line emission spectrum in detail. Yes. See you.